In this video, we're going to look at some calculations involving potential energy. And if you remember back, we have two types of potential energy. We have gravitational potential energy, which involves an object at a certain height. And then we also have elastic potential energy, which involves stretching like a spring or a rubber band, and you feel that energy that's stored when you stretch it, because when you let it go, it tries to go back to its original form. So first we're going to be looking at gravitational potential energy. And this should look familiar, especially from our STAIR lab. And potential energy, when we're talking about gravitational potential energy, is calculated by multiplying the mass times 9.81 meters per second squared multiplied by the height that that object is at. So we're going to look at a couple of examples here, and we're going to be using this formula to calculate the potential energy. So in our first question here, we have vertical velocity, which is a ride at Six Flags Great America. Vertical velocity reaches a maximum height of 45.7 meters during the ride. Find the potential energy of the 2,500 kilogram cart. And we're assuming that this is at its maximum height. So our potential energy is calculated by multiplying mgh. So the mass of the cart is 2,500 kilograms. We're going to multiply that by 9.8 meters per second squared. And then we're going to multiply that by the height in meters, which is 45.7. Okay. And when I multiply these together, let's see, 2,500 times 9.8 times 45.7. That will get us an answer of 111,9650. So a total of 1,119,650 joules. It's about the amount of energy I wake up in the morning with, excited and ready to go to school. All right, example number 2. We have 10,000 joules of energy that is stored when a 4,500 kilogram cart is sitting on top of a hill. Find the height of the hill. So this one's working a little differently. So we have our equation for potential energy, and it's asking us to find the height of the hill. So that is the h here. So to get h by itself, I'm going to divide both sides by m and g. Those are the two variables that I need to move to the other side. So before I plug any numbers in, I'm going to do my algebra first. So I've got my potential energy divided by mg, and that will give us our height. So let's plug in what we know. So our potential energy, given in the question, is 10,000 joules, and the mass is 4,500 kilograms, and we're multiplying that by 9.8 meters per second squared. So when I go to do the math here, let's see, 10,000 divided by 4,500 times 9.8. Now be careful when you enter this in your calculator. You want to put that denominator in parentheses. So it'll be 10,000 divided by, and then put the quantity 4,500 times 9.8 in parentheses. And I get 0.227 meters. Yeah, so this is a tiny little hill. This could potentially be the start of the roller coaster, where it's kind of sitting just barely above the ground. But as you can see, 10,000 joules is not really a lot of energy that's stored here. So this is, the 0.227 is a very, 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 very small hill compared to most roller coasters. This would, again, just probably be maybe at the start of the roller coaster. Or most roller coasters have, a really big hill, and then there's kind of a dip or something. I don't know, something like that. But obviously, this is a very small hill. All right, let's talk about elastic potential energy. So with elastic potential energy, again, we're talking about springs. or rubber bands or some kind of object that has some elasticity to it. So I've got a picture here, and as you can see, we've got a weight attached to a spring, and that weight is pulling down on the spring. It's stretching it out. Okay, so all springs have a value attached to them called the spring constant. Okay, the spring constant is basically a value that determines like the strength of that spring. Okay, so all springs have a spring constant to them, and they vary from spring to spring. And then x is going to be the distance that we are stretching out our spring. So let's look at an example. We have a 100 Newton meter spring. So this is our spring constant. That's the value of the spring, like the strength of the spring. So for every meter, you're going to get 100 newtons of force. So a 100 Newton meter spring is attached to a 0.15, or is stretched to 0.15 meters. Calculate the potential energy. So our potential energy, when we're talking about elasticity, is kx squared. K is our spring constant, so let's go ahead and plug that in. So 100 Newton meters. And we're going to multiply that by x squared, so 0.15 squared. So let me go ahead and punch these into my calculator. So 100 times 0.15 squared, this gives me 2.25 joules. That's it. So this is a tiny, tiny, tiny amount of energy that is stored in our spring. Most spring constants are, around that number there. So, yeah, 2.25 joules. And that is how you work through the elastic potential energy problems. Just plug and chug.